Hello, I'm Albert Merriquin, and today I'm super excited to present this important topic to many of our utility users. This presentation on high voltage arc flash for overhead conductors is based on an IEEE paper that I published about 3 years ago, titled High Voltage Arc Flash Assessment and Applications. That paper evolved into the module that we now call ArcFault. The purpose of this presentation is to provide some information on the background and industry needs for the arc flash analysis in overhead conductor systems. We will also discuss the model validation and development, plus go over some of the assumptions for its use. Later in the presentation, we will observe simulations of arc faults placed at different locations in overhead conductor systems, and also discuss the benefits of the arc fault solution as a fully integrated module within ETAP. The need of a high voltage arc flash for overhead conductor systems started based on some OSHA requirements for utilities to perform incident energy calculations for voltages above 1000 volts. Another reason is the proliferation in recent years of renewable energy systems, and in particular, their AC collector systems, which tend to operate between 17 to about 38 kV. In this section, I will present a brief overview of the theory behind the ArcFault model. As linemen approach live distribution electrical circuits, either by climbing or approaching them with boom trucks, they're exposed to shock and arc flash hazards. Once the electrical worker crosses certain approach boundaries, they're exposed to a variety of potential arc faults. In overhead conductor systems, these arc faults include unload series arcs, line to ground arcs, and less likely, but still possible, line to line and three-phase arcs. The most likely type of arc in overhead conductor systems is the line to ground arc fault. This is why NESC and OSHA have given emphasis to this type of fault and provided some basic guidance, such as is provided in the National Electrical Safety Code in table form to estimate the incident energy for this type of systems. Of course, live work tasks are not only required on distribution and transmission lines, but also in medium and high voltage substations. Single line to ground arc faults can be initiated, unfortunately, by line contaminants, by inadvertent human movement around the energized conductors, or simply by improper application of safety ground conductors. To start our discussion of high voltage arc theory, I would like to shed some light at some of the background papers which, over the past decades, provided the foundation for what is now the ArcFault module. First, we can start with the Warrington formula, which is an old formula, and for many decades, it provided a fundamental relationship between arc current and resistance, which was used by several equipment manufacturers to determine information about internal arcs in circuit breakers and other equipment. Decades later, the works of German researchers Terzier and Conkling at the FGH Mannheim laboratories provided the foundation to what we now call ETAP ArcFault Method 1, which is typically used in countries using IEC standards. Terzier and Conkling experimented with long single-phase arcs in open air, and using their test results managed to derive a relationship between the gap, current, voltage, and resistance. However, the main method used by ArcFault is based on the research performed by EPRI. Their testing served as the validation to several commercially available software products, including ArcFault. This method is currently called ArcFault Method 2, and it is the default method used by most countries in North America, including Canada, Mexico, and the US, to perform incident energy calculations for overhead conductor systems. Now let's focus our attention to the physical behavior and incident energy models of line-to-ground arc faults. This video shows the arc ignition, the arc initial length, the arc elongation and arc movement, and the general shape of the arc plasma and molecular clouds for this high voltage long arc test performed for the Bonneville Power Research Project for high voltage arcs. We can see that the heated molecular cloud rises and that the arc columns tend to move along the conductive molecular material in the cloud. The position of the electrical worker relative to the arc is critical. The arc heat flux is in fact not the highest at the current position of the mannequin. In its current position, the mannequin receives mostly radiation heat transfer up until the time the heated molecular cloud rose and made direct contact with the worker. This slide shows the main effect of the physical behavior of the high voltage arc from the previous video. The main takeaway here is that the shape of the expanded arc column and plasma for the high voltage arc resembles mostly what we can call a cylindrical shape. The shape of the arc plasma using more familiar industrial methods such as IEEE 1594-2018 is essentially a spherical. The distance from the arc to the electrical worker in this slide defined as the term R for essentially the distance between the worker and the arc. For long arcs, the incident energy versus distance relationship is approximately 1/R. The incident energy versus distance relationship of the IEEE 1584 open air models is approximately 1/R². So this essentially shows that the cylindrical shape will tend to transfer more heat towards the electrical worker. Now let's talk about the ArcFault model validation. The model equations and their validation were presented at the 2019 Electrical Safety Workshop in my paper titled High Voltage Arc Flash Assessment and Applications. It is available through IEEE Explorer. The paper talked about how the models were validated against several methods. And it showed that most high voltage arc flash methods provide reasonable incident energy calculation results. There were a few exceptions where the empirical models, such as the EPRI and Terzic Conkling, produce more realistic incident energy results than those of the theoretically derived models. Such exceptions are elaborated and described in my publication. This is one of the charts from my paper. Here we can see that most models produce between 9 to 12 calories per centimeter square as expected, based on NESC table 410-2. The Lee method introduced here clearly shows unrealistic results. Of course, this method is no longer mentioned in IEEE 1584 as a viable option to calculate the incident energy. This chart shows a few important takeaways. The first is that the Lee method produces more or way overly conservative results as the system voltage increases. The second main takeaway here that we can see is that the methods designed for high voltage arcs do not have much dependency on the system voltage. As we can observe on the x-axis, the system voltage is increasing, but based on the constant short circuit current and gap, the energy delivered is roughly about 4 calories per centimeter square. Comparisons against IEEE research papers and other cited publications are also included in my paper. And they show that the ArcFault methods have great correlation with all the other methods available out there, which have been suggested in the past for the determination of incident energy in overhead conductor systems. All, of course, with the exception of the Ralph Lee method, shown in green color here, which shows overly conservative results. Now, I would like to give you a live demo of simulations of arc faults in overhead conductor systems. This particular system in ETAP shows a transmission system delivering power across different utilities, different industrial sites and manufacturing facilities. So let's take a quick look at the overall layout where we see different industrial plants,
different generation facilities, different utility connections scattered throughout the electrical grid. This particular example is good because we have different voltage levels. Let's look at some of the voltage levels available where we can introduce the ArcFault module. We have an open air substation with 132 kV or 132 kilovolt transmission systems feeding the substation. Other portions of the system show 220 kilovolt transmission lines and different locations. Some of these locations are going to be used for the analysis of line to ground arc faults, as we will show in a few minutes. But before I actually get to the demo of the program, let me show you how it is integrated into the ArcFlash products. So once you switch into the ArcFlash calculation, you'll have your choice of methods by simply going into the study case. So for this particular example, we have created study cases related to ArcFault and also for IEEE 1584 or Lee or other available methods. So let's go ahead and inspect an ArcFault created study case. So we can simply click on the suitcase icon, and after we get the study case open, we can focus on the method tab. Here under the ArcFlash method tab, we can see that there are three options: the NFPA 70E Annex D 2 and 3, which is a very old method, pretty much superseded by IEEE 1584 2002. We have the actual 1584 calculation methodology, and we have the ArcFault methodology. Since we're talking about ArcFault, we can observe that now we have the model simulation, ArcFault, line to ground, line to line, and three-phase. We also have the solution method, and as I mentioned during the introduction and background on the methodology, we have method 2, which is the EPRI high voltage arc flash work, and once you click on it, you'll be able to see and have direct access to the equations, to the voltage gradient coefficients, thermal flux coefficients, and all the different parameters that are used to get the behavior of the arc. At the same time, since it's fully integrated into ETAP, you'll have the ability to specify how the arc duration, or also commonly known as fault clearing time, is obtained for ArcFault. Just like for 1584, the program automatically determines the protected device operating time. Now, one thing that will become obvious as we see during the simulations is that ArcFault not only responds to phase over current protected devices, but it also responds to any kind of positive, negative, and zero sequence protected devices, which is typically what occurs when you have a line to ground arc fault in a power system. The remaining options for parameters such as automatic gaps, working distance, typical values, incident energy levels for providing a range of the energy at different circuits, they're all available and are part of the ArcFault module. Let's take a quick look at one more editor before I actually show you how the program works. The ArcFault program relies on a couple of different editors, which we're going to talk about next. In particular, the ArcFault minimum approach distance. This editor, it's a summary of the recommendations in the National Electrical Safety Code related to the minimum approach distances for energized work on line to ground and line to line circuits. What's really important here is to also recognize that these distances vary as a function of the transient over voltage conditions which could occur, and it's very common in distribution and transmission systems. Sources of transient over voltage conditions include lightning, the operation of protected devices as loads are added or released from the electrical grid. Once you determine the level of over voltage conditions, you can see that these distances vary. So for lower voltage conditions, the distances are smaller or shorter. Therefore, the typical gaps and working distances will be less, and therefore the energy values will be calculated accordingly. Next, what we'll do is we'll actually launch the simulation, and we'll launch it in a couple of different ways. I like to start by faulting a few hundred locations. So by simply selecting a previously created study case where we have several locations through our transmission system, we're going to proceed to do an ArcFault analysis for line to ground conditions throughout the grid. So as soon as we select this, we can proceed to select a particular report and perform a simulation. While this simulation runs and performs these hundreds of analyses, which include the operation of protected devices and different elements throughout your system protection, we can see that the program has now performed all this analysis, and similar to our previous ArcFlash modules, it provides annotations for results right on the one-line diagram that show us the incident energy and the other results such as the clearing time, the ArcFlash boundary, and the working distances. Of course, this 48.4 inch is calculated based on the National Electrical Safety Code recommendations and equations. As we can see now, of course, we've faulted hundreds of locations, and of course, I know we will expect to have a powerful filtering analysis tool just like we have for ArcFlash using IEEE 1584. So if we proceed to open the ArcFlash Analyzer, we'll be able to see that all the tools available for ArcFlash using 1584 are also available for the ArcFault module. We see all the different voltage values. We can see the incident energy values filtered and sorted throughout the system. We can choose to focus and filter onto higher energy areas or trouble areas for different conditions, and all the familiar filters and analysis tools that are provided by ETAP in the ArcFault Result Analyzer. Now, let's proceed to show a simulation of the operation of protected devices. Let's zoom out into a particular portion of our system where we have a couple of transmission lines, 220 kV lines, and we're going to switch our study case to perform a single arc fault on either one of these two parallel 220 kV lines by simply clicking on the fault insertion for three-phase line to ground, line to line, or three-phase arc faults. We can click on it and drop the fault on any location we want. In this case, I'm going to be faulting it on bus 63, which is a location along this 220 kV transmission line. As we can see, the operation of the two protected devices at the substations on either end of the transmission line, and after both devices operate, we have the de-energization of the arc fault. We can reduce the speed of the flashing down to 0 so that we can focus now on the results of the simulation. What I would like you to pay attention to is the displayed currents and results on the one-line diagram. We are currently displaying the sequence current values, which represent positive, negative, and zero sequence currents which would flow in that transmission line system in the event of a line to ground arc fault, including the effect of the arc resistance and arc voltage. We could easily switch to the phase values. Now we have phase A, B, and C fault currents. Or we can switch to the zero sequence currents only to determine what part of our circuit has grounded elements and which one doesn't. All combined, these positive, negative, and zero sequence currents can be used to determine the operation of both phase and ground protected devices. As we can see from our ArcFault viewer, a fault at this location has caused the operation of two types of protected devices. On one end, at one of the substations, circuit breaker 101 was stripped by relay 4 using the ground over current 1 instantaneous function. On the other end substation, with circuit breaker 880, the fault was cleared by the operation of relay 2 using a phase over current type 51 protection. and the end result is that the arc fault was de-energized. In this case, two sources were energized in the fault. After both sources are de-energized, the fault is clear. Now, there is a tremendous value to being able to analyze the results from the point of view of the operation, because obviously transmission and distribution systems may involve some complex operations for their protected devices.
To conclude, we've seen that high voltage arcs have predictable behavior, and such behavior can be approximated using mathematical relationships such as those developed by Warrington, Terzian Conglin, and also published in research work by EPRI and Bonneville Power and others. We also observed that high voltage arcs are mainly influenced by short circuit current and gap, which is the gap between the electrodes or conductors. And we've also seen that the system voltage has little effect, maybe less than 2% or less. We also talked about the heat flux and how it showed dependency on the gap length because of its somewhat cylindrical shape of the arc plasma molecular clouds. This is an important concept for us to understand that the heat transfer model of a long arc is very different from that of more established industrial standards such as IEEE 1594-2018. We saw during the live demo that the ArcFault model contains two methods which were developed based on actual test results. And we saw that ArcFault is a fully integrated module along with the short circuit and protected device coordination, which will help us to reduce human error factors in the incident energy calculations. ArcFault models can be used to perform incident energy calculations for faults other than single phase, line to ground, and such information is described in publications, including mine. So you could follow up and read on that application. With that, I would like to say thank you very much for your time. And at this time, I would like to suggest that you submit questions to the chat, which can be answered during our expert panel session. Thank you very much.